Two things have been happening for a very long time. For 23 centuries, going back to a Greek philosopher who argued a runner could never catch a tortoise, some of the sharpest minds available in any given era have kept finding the exact same kind of crack. An argument built from steps that each look completely sound, arriving at a conclusion that plainly cannot be true. At the same time, on a much smaller and far more everyday scale, ordinary systems have been quietly built and run on that very same sound-looking logic, by people who never noticed where it was cracked. A city adds a new road to ease traffic, and every commute gets slower. A village shares a pasture, and sheep by entirely reasonable sheep wears it down to dirt. 100 voters, each one perfectly consistent, produce a group choice that is not consistent at all. This is a collection of 50 such moments, gathered from mathematics, physics, economics, and plain daily life, one settling in after another. A few are old enough to predate most of written history. One comes from a Texas porch on a hot afternoon in 1974, and a couple are still being argued over by working physicists tonight somewhere. None of them need to be solved for you to get something real out of sitting with them. There is no reason to hurry through any of it. Settle in. These have waited a couple of thousand years already, and every one of them will still be exactly this strange by the time you reach the last one. There is a boat in an old Greek story that never sinks and never rots, because every time a plank wears out, the crew simply replaces it. Sail it long enough, and one plank at a time, every original piece of timber is gone. The hull holds the same shape, does the same work, carries the same name. So here is the question sailors and philosophers have argued over for roughly 2,000 years. Is it still the same ship? Plutarch recorded the puzzle almost in passing, describing the Athenians' habit of maintaining the vessel that supposedly carried Theseus home from Crete by continually renewing its aging boards. He noted, almost as an aside, that some philosophers already used it as an example in disputes about identity and change, which tells you the argument was old even in his own time. The intuitive answer feels obvious both ways at once. Of course it is the same ship, you say, since nothing ever happened to it except ordinary maintenance, the kind every ship gets. And yet not one atom of the original vessel survives, so in what sense is any of it still there? Philosophers have offered different escape routes. Some argue identity lives in form and function rather than material, so a ship that keeps sailing and keeps its shape stays the same ship regardless of what it is built from. Others argue identity requires continuous physical stuff, in which case the plank-by-plank ship really has become something new, however gradual the change. A third answer just accepts that our language for sameness was never built to handle gradual total replacement cleanly, and stops expecting a tidy verdict. The puzzle is not really about boats. Nearly every cell in a human body is replaced over the course of a life, some in days, some over years, so the person reading this sentence is, materially, mostly a different collection of matter than the child who first learned to read. A person's beliefs, memories, and habits undergo something similar, worn down and rebuilt piece by piece, until very little of the original remains except the felt sense of being the same one who started. The ship is still called Theseus, whatever timber happens to be holding it together this year. Somewhere over lunch at Los Alamos in 1950, a physicist named Enrico Fermi asked his colleagues a question that still has no settled answer. They had been joking about flying saucers, and Fermi, doing the kind of quick mental arithmetic he was famous for, stopped and asked, "Where is everybody?" The galaxy holds hundreds of billions of stars, many of them billions of years older than the sun, plenty of time for at least one civilization to have developed the ability to travel between stars. Even at a small fraction of the speed of light, a spacefaring civilization could cross the galaxy in a few million years, colonizing as it went. A few million years sounds enormous until you set it beside the age of the galaxy itself, which is thousands of times older. By Fermi's math, the galaxy should already be full, or should at least show some trace of having been visited. Instead, decades of careful listening with radio telescopes have turned up nothing. Proposed answers span a wide range. Some argue that intelligent life is simply rare, that the specific chain of accidents leading from chemistry to biology to complex thought may not repeat easily elsewhere. Others propose a great filter, some barrier so difficult to pass, whether the origin of life itself or the survival of a technological civilization past its own most dangerous inventions, that almost nothing gets through it. Still others suggest civilizations do exist, but stay quiet on purpose, or communicate in ways we simply have not learned to detect yet, or burn out and collapse before they ever spread far. None of these explanations has enough evidence behind it to close the question, and each one implies something different about how rare or fragile a civilization like ours might be. What makes the silence unsettling is not that it proves anything. It proves nothing at all, and that is precisely the trouble. A universe old enough and vast enough to expect company has offered none, and every explanation on the table asks us to imagine either that we are far rarer than we assumed, or that something eventually goes wrong for civilizations like ours. The radio telescopes are still listening, pointed at a sky that has not answered yet. 3 closed doors sit on a game show stage. Behind one sits a car, behind the other 2, a goat. You pick a door, and before it opens, the host, who knows exactly what is behind every door, opens a different one to reveal a goat. Now he asks whether you'd like to switch to the remaining closed door or stay with your original pick. Most people's gut says it no longer matters, that the odds are now simply 50-50 between the 2 doors left. The gut is wrong. Switching wins twice as often as staying does. The puzzle takes its name from Monty Hall, who hosted the American game show Let's Make a Deal for decades, though the scenario itself is a simplified version of the choices contestants actually faced. When the columnist Marilyn Vos Savant published the correct answer, that switching wins about 2/3 of the time, in her magazine column in 1990, the backlash was enormous. Thousands of readers wrote in to say she was mistaken, including, by her own later account, close to 1,000 people holding PhDs, some of them mathematicians. Computer simulations run over and over eventually settled the argument in her favor. The reasoning becomes clearer once you separate the host's knowledge from pure chance. When you first pick a door, there is a 1 in 3 chance it hides the car, and a 2 in 3 chance the car is behind one of the other doors. That 2/3 probability does not vanish when the host opens a door, because the host is not picking randomly. He always avoids the car and always avoids your door, so opening a goat door does not spread the odds evenly. It concentrates the entire 2/3 probability onto the single remaining door you did not pick. Switching effectively lets you claim both of the doors you did not originally choose, filtered down to the one that survived. The puzzle keeps surprising new audiences precisely because human intuition treats probability as if it resets with each new piece of information, when here, it very deliberately does not. 2 goats in a car, and the smartest move was never about luck at all, only about paying attention to what the host was forced to reveal. A patch of common grazing land sits at the edge of an old English village, open to every herder who wants to graze an animal there. No single herder owns it, so no single herder bears the full cost of wearing it out. Each one reasons privately that one more sheep added to their own small herd barely dents the grass, while the extra milk or wool it provides is theirs alone to keep. Every herder in the village reaches the exact same private conclusion, and the shared pasture is stripped bare within a season or 2, worse off for everybody who depended on it. The economist William Forster Lloyd described this exact scenario in a lecture in 1833, using it to illustrate a flaw hiding inside otherwise sound individual reasoning. The ecologist Garrett Hardin gave the pattern its lasting name in a 1968 essay, calling it the tragedy of the commons, and used it to argue that some shared resources need either regulation or private ownership to avoid being consumed past the point of recovery. The mechanism is not about greed exactly, or not only about greed. It works even among reasonable, moderate people, because the math facing each individual user genuinely does favor taking a little more, right up until everyone's version of a little more adds up to a lot. The pattern recurs anywhere a valuable resource is shared and hard to fence off. Fishing fleets working the same open waters have driven stock after stock toward collapse, each captain rational in isolation. Drivers merging onto an already congested highway each save themselves a few minutes while adding delay to everyone behind them. Farmers drawing from a shared underground aquifer can each justify one more well long after the water table has started falling for good. In every case, the resource belongs to everyone, and a resource that belongs to everyone can end up in practice cared for by no one in particular. Later economists, including the political scientist Eleanor Ostrom, pointed out that real communities have often managed shared resources successfully for generations without either full privatization or heavy state control, using their own local rules and mutual monitoring instead. Left with no such rules at all, though, the old pasture keeps getting stripped bare, one entirely sensible sheep at a time. Suppose a working time machine existed, and suppose someone stepped into it, traveled back decades before their own birth, and whether by accident or design, prevented their grandparents from ever meeting. That single act would erase the chain of events that eventually produced the traveler in the first place. But if the traveler was never born, they never grew up, never built the time machine, and never made the trip back to interfere with anything at all. Which means the grandparents would have met after all, which means the traveler would be born after all, which means the trip would happen after all. The loop closes on itself and refuses to settle anywhere. The scenario has circulated among philosophers and science fiction writers since at least the early 20th century, valued less as a prediction about real travel and more as the cleanest way to show what a working time machine would actually break. Ordinary cause and effect assumes a clear direction, a cause happening before its effect, with no way for a later event to reach back and undo an earlier one. A time machine capable of altering its own past would need effects that can erase their own causes, and a universe that permits that kind of contradiction stops behaving in any predictable way at all. Physicists who take the mathematics of time travel seriously, largely within the framework of Einstein's general relativity, have proposed a few ways such a universe might avoid actually breaking. One idea holds that only self-consistent loops are physically allowed, meaning a traveler could go back and take part in events, but only in ways that were already quietly part of history all along, never in ways that create a true contradiction. Another idea proposes that any change spins off an entirely separate branching timeline, leaving the original one and the traveler's own past untouched. Both are ways of letting the mathematics permit time travel without permitting genuine paradox. No one has ever built a machine to test any of this, which is itself a small comfort. The grandfather paradox survives for now, purely as a thought experiment sharp enough to keep physicists honest about what their own equations quietly allow. A tortoise challenges the swiftest runner in Greek legend to a foot race and asks for a small head start, since everyone already knows how the race will end. Achilles agrees, amused, but the philosopher Zeno of Elea, writing around the 5th century before the Common Era, argued that Achilles could never actually catch the tortoise at all, however fast he ran. Here is the argument. By the time Achilles reaches the point where the tortoise started, the tortoise, however slowly, has crawled a little further ahead. By the time Achilles reaches that new point, the tortoise has advanced again by some smaller distance. This repeats without end. Every time Achilles closes one gap, a new, smaller gap has already opened in its place. An infinite number of gaps stand between Achilles and the tortoise, and it seems, on the face of it, that you cannot cross infinitely many gaps in a finite amount of time. Zeno was not actually trying to prove tortoises unbeatable. He was one of several thinkers using paradoxes like this one to argue, against common sense, that motion and change might themselves be illusions, that a fully coherent picture of the world had to be a static, unchanging one. The paradox went unresolved in any rigorous sense for well over 2,000 years, not because the answer was hidden exactly, but because the mathematics needed to state the answer cleanly did not exist yet. That mathematics arrived with the development of calculus in the 17th century, which showed that an infinite sum of shrinking numbers can still add up to a perfectly ordinary finite total. Each gap Achilles closes is smaller than the last by a consistent ratio, and that shrinking sequence of distances and the shrinking sequence of time it takes to cross them both converge neatly to a single finite point, the exact moment Achilles overtakes the tortoise. Infinity, it turns out, is not the same thing as endlessness in time. You can fit an infinite number of ever smaller steps into a perfectly finite stretch of both distance and time. Achilles wins the race, exactly as everyone always expected, and the tortoise's real gift to philosophy turned out to be a question about infinity that took 2 millennia to properly answer. 2 people are arrested together and held in separate interrogation rooms, unable to speak to each other or coordinate a story. Each is offered the same private deal: betray your partner and you go free, while they take a long sentence, unless they betray you too, in which case you both get a moderately harsh sentence. Stay silent and cooperate with your partner's silence, and you both get a light sentence, but only if neither one talks. Alone in a room, thinking it through, each prisoner reaches the same cold logic. Whatever the other one does, betraying is the better move for me personally, so betraying is the safer bet regardless. The scenario was formalized at the Rand Corporation in 1950 by the mathematicians Merrill Flood and Melvin Drescher, and named the prisoner's dilemma shortly after by their colleague Albert Tucker, who built the prison story around a piece of mathematics his colleagues had been studying under a drier name. What makes it interesting is not the crime story at all, it is the shape of the incentives underneath it. Betrayal is what mathematicians call a dominant strategy. It produces a better outcome for you than staying silent would, no matter which choice the other person makes. Since both prisoners can work through that same reasoning independently, both choose to betray, and both end up serving the moderately harsh sentence, a worse outcome for each of them than if they had simply trusted each other and stayed quiet. The frustrating part is that neither prisoner did anything irrational. Each one made the individually correct choice, given what they knew and could not verify about the other. It is the combination of two individually sound choices that produces a jointly bad one, which is a very different failure than simple foolishness or greed. The same structure shows up wherever trust is hard to confirm and defection carries a private reward. Countries locked in arms races, where each one privately gains from building more weapons regardless of what rivals do. Businesses locked in price wars, where each privately gains from undercutting regardless of what competitors charge. And any negotiation where a handshake deal cannot quite be enforced. Cooperation in situations shaped like this one turns out to require something outside pure self-interested logic. A reputation, a relationship, or a rule, since logic alone keeps landing both sides in the cell they were trying to avoid. City planners in Stuttgart, Germany, once added a new street to relieve pressure on a congested part of the road network, confident it would help. Travel times across the city got worse instead, and only improved again once the new street was closed. Seoul removed an elevated highway through the middle of the city years later, expecting more congestion elsewhere, as displaced traffic scattered, and again overall traffic flow improved. Both cities had stumbled into the same counterintuitive mathematics. The mathematician Dietrich Bross described the underlying effect in 1968, while studying networks in which every driver independently chooses whatever route looks fastest to them personally, with no central authority assigning routes for the good of the whole system. A new road added to such a network looks like an obvious improvement, since it gives drivers one more option, and options should only ever help. The trouble is that every driver reasons the same way, and if the new route looks appealing to enough of them individually, they all pile onto it and onto whatever roads it happens to connect to. Those connecting roads become the new bottleneck, and the total time everyone spends in traffic can rise, even though each driver, taken alone, only ever chose the route that looked fastest to them in the moment. This is close cousin to a much older idea in economics called an equilibrium that is not actually optimal, a system where nobody can improve their own outcome by unilaterally switching strategy, but where the overall result is still worse than some other arrangement everyone could have reached together. Left to purely individual choices, a road network can settle into exactly this kind of stable but inefficient traffic pattern, and removing an option, closing a road, can jolt the system out of that bad equilibrium into a better one, simply by taking away the shortcut that had been quietly luring everyone into the same jam. Transportation engineers now model networks specifically to check for this effect before building new connections, since intuition alone, more roads must help, keeps turning out to be an unreliable guide. Somewhere in a city right now, a perfectly good stretch of asphalt is very possibly making everyone's drive home a few minutes longer than it needs to be. Stand in front of a supermarket shelf stocked with 24 kinds of jam, and something strange happens. Shoppers slow down, linger, compare, and often walk away having bought nothing at all. Cut the same shelf down to 6 kinds of jam, and buying rates climb, and the people who do buy report feeling more satisfied with what they chose. More options, it turns out, do not reliably make people happier, even though every added option should, in theory, only ever make the best possible choice more available. The psychologist Barry Schwartz brought this idea to wide public attention in his research, and later a book built around it, arguing that every additional option adds a small mental cost alongside whatever benefit it offers. Each new choice has to be weighed against every other one, which takes real cognitive effort, and each one left unchosen leaves behind a faint nagging thought that some rejected option might secretly have been the better pick. Psychologists call this a kind of counterfactual regret, the quiet cost of wondering what you missed, and it tends to grow right alongside the size of the menu you were choosing from. A shopper picking between 6 sensible jams can feel confident in whatever they grab. A shopper picking between 24 can feel paradoxically less sure of a choice that objectively had more chances of being a good one. The effect shows up well beyond grocery aisles. Retirement plans offering dozens of investment funds see lower enrollment than plans offering a handful of well-chosen defaults. Dating profiles with an overwhelming number of nearby matches can leave people less likely to commit to any single one. Even something as ordinary as a restaurant menu can tip from inviting into exhausting once it passes a certain length, the promise of variety quietly curdling into the burden of comparison. None of this means choice itself is the enemy, since having no options at all is its own kind of unhappiness. The lesson retailers and designers eventually took from the research was narrower and more useful than that. A smaller, thoughtfully curated set of good options can leave people happier than an enormous pile of choices ever could. Because somewhere past a certain point, one more option stops being a gift and starts being a small tax on everyone who has to look at it. One twin boards a spacecraft capable of traveling near the speed of light, journeys out to a distant star, and returns home. The other twin stays on Earth the whole time. When the traveler finally steps off the ship, decades appear to have passed on Earth, yet the traveler has aged only a few years. The two siblings born on the same day are no longer close to the same age. The scenario follows directly from Albert Einstein's theory of special relativity, published in 1905, which showed that time itself does not tick at a single universal rate, but depends on how fast something is moving relative to something else. At speeds close to light, the effect called time dilation becomes large enough to matter enormously. At ordinary human speeds, it exists but is far too small to ever notice. At first glance, the scenario looks like it should not work as described, since from the traveling twin's own point of view, it is the Earth and the stay-at-home twin that seem to be racing away and back again. If motion is only ever relative, why should one twin end up younger rather than both simply seeing the other as older? The asymmetry that breaks the tie is acceleration. The twin who stays on Earth moves at a constant, unchanging velocity the entire time, while the traveling twin has to accelerate away from Earth, decelerate to turn around, and accelerate again to come home. Changes in motion the stay-at-home twin never experiences. That difference in what physicists call reference frames is what allows the two clocks to genuinely disagree by the end of the trip, rather than each twin simply seeing an illusion in the other. This is not only a thought experiment. Atomic clocks, precise enough to detect fractions of a second of drift, have been flown on ordinary aircraft circling the globe and compared afterward against identical clocks that stayed on the ground. The airborne clocks came back very slightly behind, exactly the tiny effect relativity predicted, measured directly rather than merely calculated on paper. The traveling twin steps back onto Earth, having genuinely lived through less time than the one who waited, and the gap between them is not a trick of memory or perception, but a real difference etched directly into the ticking of two separate clocks. A photographer working on a project documenting coastal erosion in California posted an aerial photograph online in the early 2000s, one image among 12,000 others in the collection, showing a stretch of cliffside homes from above. It had been viewed a handful of times. Then the entertainer Barbra Streisand, whose home happened to appear in the frame, filed a lawsuit in 2003 demanding the photograph be taken down, citing privacy. Word of the lawsuit spread through news coverage, and within a month, that same barely noticed photograph had been viewed several 100,000 times. The pattern now carries her name, even though she was hardly the first to run into it, and it has repeated often enough since to count as a reliable rule rather than a one-off embarrassment. The mechanism is fairly simple once you see it laid out. Most information left alone only interests the small audience it was already relevant to. An attempt to suppress that information adds a second, much larger layer of interest on top of the first. Curiosity about why someone wanted it hidden badly enough to fight over it. That second layer of curiosity, fueled by the suspicion that something worth hiding must be worth seeing, often dwarfs whatever attention the original material would have drawn on its own. And news coverage of the suppression attempt does the rest of the work by advertising the very thing it describes. Companies have repeated the mistake with product complaints, threatening legal action over a single critical blog post, and watching the criticism go viral as a result. Governments have repeated it with leaked documents, drawing far more global attention to a story by publicly denouncing it than quiet silence ever would have. Even individuals occasionally trigger a small-scale version of it, discovering that an angry public correction to a minor rumor spreads the rumor itself further than it would ever have traveled unchallenged. None of this means suppression never works. Plenty of quiet legal takedowns succeed without anyone noticing at all. The pattern only bites when the suppression itself becomes visible and newsworthy, at which point the thing someone tried to bury tends to end up standing in considerably brighter light than it started in. A cat sits sealed inside a closed box, alongside a small amount of radioactive material, a detector, and a mechanism rigged so that if the material happens to decay, a hammer breaks a vial of poison and the cat dies. If it does not decay, nothing happens and the cat lives. The radioactive decay itself is a genuinely random quantum event, with precisely equal odds either way, and by the strict mathematics of quantum theory, until someone opens the box and looks, the undecayed and decayed states exist together, blended, unresolved. Which means the cat inside, by that same strict mathematics, is neither simply alive nor simply dead, but some blend of both, until the box is opened. The physicist Erwin Schrödinger proposed the scenario in 1935, and he did not intend it as a serious description of how cats actually behave. He meant it as a pointed criticism, a way of taking an idea that sounded reasonable at the scale of a single atom and dragging it up to the scale of an ordinary household object to show how absurd the result became. At the level of individual particles, this blending of two states at once, technically called superposition, is not speculation. It has been confirmed directly and repeatedly in laboratories, in electrons, photons, and other tiny objects that really do behave as though they occupy two possibilities simultaneously until a measurement forces one outcome to become real. Schrödinger's whole point was that nothing in quantum theory's own equations explains why that blending should ever stop mattering once you scale the setup up to something the size of a cat. Physicists still disagree about where exactly the line falls and about what measurement or observation even really mean at a physical level, since a measuring device is itself, after all, just another arrangement of atoms obeying the same quantum rules. Some interpretations argue the cat really is in an odd combined state until observed. Others argue the blending collapses long before it ever reaches the scale of a cat, for reasons the mathematics does not fully spell out. Nearly a century on, the thought experiment Schrödinger invented specifically to expose an absurdity is still the sharpest tool physicists have for explaining exactly where their own theory stops making obvious sense. A university once found itself accused of favoring men in graduate admissions, based on numbers that looked damning. A noticeably higher acceptance rate for male applicants than female ones across the school as a whole. When researchers broke the data down department by department, though, something odd emerged. Nearly every individual department was actually admitting women at an equal or slightly higher rate than men. The overall number and the department by department numbers were both accurate, and they told opposite stories. The explanation lay in where applicants had chosen to apply, not in how they were evaluated once they got there. Women had applied in disproportionately large numbers to the university's most competitive, lowest acceptance departments, while men had applied in disproportionately large numbers to departments with far higher acceptance rates overall. Combine every department into one big pooled number, and that uneven pattern of where people applied ends up dominating the result, completely burying the fact that each department taken on its own was treating men and women about the same. The statistician Edward Simpson described this kind of reversal formally in a 1951 paper, though earlier statisticians had noticed versions of the same trap decades before him. It happens whenever a hidden variable, in the admissions case, which department someone applied to, is distributed unevenly across the groups being compared, and that hidden variable also happens to be strongly linked to the outcome being measured. Combine the groups without accounting for it, and the combined number can point in a direction that every one of its own component parts actually contradicts. The same reversal has turned up in medical studies, where a treatment can look worse overall, while genuinely outperforming the alternative in every age group studied, once the mix of patients within each group is properly accounted for. It shows up in sports statistics, in hiring data, in almost any data set built by combining smaller groups of very different sizes and different baseline rates. A single tidy number sitting at the top of a report can feel like the whole story. Simpson's paradox is the standing reminder that the tidy number sometimes only exists because a much messier and more honest story is hiding just one layer beneath it. Write down a single short sentence. This statement is false. Now try to decide honestly whether it is true. If the sentence is true, then what it says must be accurate, and what it says is that it is false, so it has to be false. But if it is false, then what it claims is inaccurate, and it claims to be false, which would make it true after all. Every path through the logic loops straight back into its opposite, with no stable place to land. Ancient Greek thinkers were already circling versions of this puzzle, and its clearest early form is generally credited to the philosopher Eubulides of Miletus, writing in the 4th century before the Common Era. What makes the sentence break, when ordinary sentences do not, is that it talks about itself. An ordinary true or false statement describes something out in the world, the weather, a fact about history, the color of an object, something the sentence itself stands entirely apart from. This one instead loops back and makes a claim about its own truth value, and that small twist is enough to unravel the whole thing, since there is no outside fact left to check it against. Logicians took the problem seriously enough to build entire careers around containing it. The 20th century logician Alfred Tarski developed a formal framework for talking rigorously about truth, partly in response to puzzles exactly like this one, distinguishing between a language that describes the world and a separate higher-level language used to talk about truth within that first language, specifically so that a sentence could never simply reach back and make a claim about its own truth in the same breath. Mathematicians ran into a close cousin of the same trouble when building the foundations of set theory, where self-reference produced contradictions just as sharp as this one, forcing similarly careful rules about what a system is and is not allowed to say about itself. The liar sentence itself was never solved so much as fenced off, walled away by careful rules that keep ordinary language and mathematics from tripping over their own reflection. It sits there still, a single short sentence, calmly refusing to be either one thing or the other. You are shown 2 boxes. The first is transparent and always contains a modest, guaranteed sum of money. The second is opaque, and its contents were decided before you ever walked into the room by a predictor with a long track record of guessing people's choices correctly. If the predictor guessed you would take only the opaque box, it was filled with a fortune. If the predictor guessed you would take both boxes, it was left empty. You may take only the opaque box, or you may take both. What do? The physicist William Newcomb devised the puzzle in the 1960s while thinking through problems in decision theory, and the philosopher Robert Nozick introduced it to a much wider audience a few years later in an essay that has kept philosophers arguing ever since. The dilemma splits people because 2 entirely reasonable ways of thinking about it point in opposite directions. One argument says take both boxes. Whatever is in the opaque box was decided in the past and cannot be changed by anything you do now, so grabbing the visible guaranteed money on top of it can only ever help, never hurt. The other argument says take only the opaque box, since the predictor has a strong track record of guessing correctly. The kind of person who reasons their way into taking both boxes is exactly the kind of person the predictor would have anticipated and left the fortune-holding box empty for. What makes the puzzle genuinely difficult rather than merely tricky is that both lines of reasoning are internally consistent, and each one is drawn from a real, respected school of thought in decision theory. One camp insists your current choice cannot retroactively affect a decision the predictor already made, so dominance reasoning, taking the option that is better regardless of the other's contents, should win. Another camp insists that if the predictor really is reliable, then choosing to take only one box is itself strong evidence that the box was filled, so the choice and the prediction are not as separate as the first camp assumes. Decades of philosophical argument and no shortage of published papers taking each side have failed to produce a decision theory that both camps accept as correctly resolving it. People who actually test the scenario as a psychological experiment, minus the impossibly perfect predictor, tend to take only one box when told the forecaster has been reliable before, and those people on average come out richer for it. 23 strangers walk into a room, and before anyone compares notes, there is already a better than even chance that two of them were born on the same day of the year. Not the same year, just the same calendar date out of 365 possibilities. Most people guess the true number needed for even odds is much higher, closer to half of 365, since that is roughly the intuition most of us reach for, without thinking too hard about it. The mistake is in what gets compared. When you imagine checking for a shared birthday, it is natural to picture comparing yourself against everyone else in the room, which for a group of 23 is only 22 comparisons, not nearly enough to expect a match. But a shared birthday can occur between any two people in the room, not just between you and someone else, and the number of distinct pairs among 23 people is far larger than 22. It works out to 253 separate pairs, each one an independent small chance of a match, and 253 chances, even at long individual odds, is enough collectively to push the overall probability of at least one match above 50%. Push the room size up further, and the odds climb fast. At 40 people in a room, the chance of a shared birthday is well above 90%. At 70, it is above 99%, essentially a certainty, even though 70 is still a tiny fraction of the 365 possible birthdays available. The whole effect comes down to how quickly the number of possible pairs grows as a group grows, far faster than the group size itself does, a mismatch between our gut sense of scale and the actual arithmetic underneath it. The same counting principle, that the number of possible matching pairs grows far faster than the number of items being compared, turns out to matter well beyond party trivia. Cryptographers use exactly this logic, sometimes called a birthday attack, to find hidden weaknesses in systems that were assumed to be safe from collision, precisely because a security designer's gut sense of how many attempts a matching flaw would require can be just as far off as anyone's guess about a room full of birthdays. A new promotion, a bigger apartment, a long-wanted purchase, each one delivers a real lift in mood the week it happens. Come back a few months later and, more often than expected, that lift has quietly faded, and the person is back to roughly the mood they started with, just with nicer surroundings. The mind, it turns out, is remarkably good at making almost any new normal feel, eventually, like nothing special at all. The psychologists, Philip Brickman and Donald Campbell, described the underlying mechanism in the 1970s, framing it as a kind of adaptation level. People do not judge their circumstances against some fixed, permanent standard. They judge them against whatever they have recently gotten used to. A raise feels wonderful against the backdrop of the old salary, right up until the new salary becomes the backdrop itself, at which point the same amount of money stops registering as anything unusual. The mind keeps quietly resetting its own baseline to match whatever has become familiar, which means the goalposts, for what counts as a pleasant surprise, keep sliding forward, just out of reach. The same adaptation runs in the other direction too, which turns out to be the more comforting half of the finding. People facing real hardship, the loss of a job, a serious injury, a difficult diagnosis, consistently predict they will feel devastated for far longer than they actually do. Well-being researchers have found, again and again, that people tend to recover a meaningful share of their prior baseline mood within months, not years, even after events that felt at the time unrecoverable. The same mental machinery that quietly steals the shine off good news is in a fairer trade than it first seems, also working to soften the weight of bad news. None of this means circumstances are meaningless, since some changes really do move the baseline itself, not just the mood sitting on top of it. But for most ordinary ups and downs, the treadmill metaphor holds uncomfortably well. Plenty of motion, plenty of effort, and a body that keeps ending up, before too long, standing in roughly the same place it started. A family sits on a porch in Coleman, Texas, on a hot summer afternoon, content to stay put and play dominoes. Someone mentions almost idly that it might be nice to drive to a cafeteria in Abilene, 50 miles away, for dinner. Nobody particularly wants to go, but each person, reading a little enthusiasm into the suggestion that was not really there, agrees rather than seem difficult, and the family piles into a hot, unair-conditioned car for a long, uncomfortable round trip. Only once they are back home, exhausted, does someone admit they never wanted to go in the first place, and it turns out neither did anyone else. The management expert Jerry Harvey told this story from his own family in a 1974 paper, using it to name a pattern he saw constantly in the organizations he studied. He called it the Abilene Paradox, a group reaching unanimous agreement on a course of action that not one individual member actually wants, purely because each person misreads polite agreement from the others as genuine enthusiasm. It is a subtly different failure than simple peer pressure or groupthink, where people quietly suppress real disagreement because they fear consequences for speaking up. Here, nobody is afraid of anything in particular. Nobody is bullied into silence. Each person simply assumes their own reluctance is a private, unusual reaction and stays quiet rather than risk seeming like the one person unwilling to go along with what looks, from the outside, like everyone else's idea. Harvey argued that managing this kind of false agreement is a genuinely harder organizational skill than managing open conflict, precisely because there is no obvious tension to notice or resolve. A team can spend real resources committing to a plan that a private poll would have revealed nobody wanted, and by the time anyone admits it, the resources are already spent. The fix he recommended was almost embarrassingly simple: build in a habit of directly asking people what they actually think, rather than trusting the smooth, agreeable silence that a room can produce all on its own. The cafeteria in Abilene was, by every account, perfectly decent. It was also, for one family on one hot afternoon, a 50-mile detour that nobody had ever wanted to take. Step outside on a clear night and look up. Between the stars, the sky is dark. That fact seems obvious enough to not need explaining, right up until you take a simple assumption seriously. If the universe is infinite in size, filled evenly with stars in every direction, then no matter which direction you look, your line of sight should eventually run into the surface of some star, however distant. An infinite number of stars, scattered through an infinite universe, should overlap to fill the entire sky with light, leaving no dark gaps between them at all. And yet the gaps between the stars stay dark. Something about that simple assumption has to be wrong. The astronomer Heinrich Wilhelm Ohlbers popularized the puzzle in an essay in 1823. Though the tension had bothered earlier thinkers too, including the astronomer Johannes Kepler 2 centuries before him, who used the darkness of the night sky as evidence that the universe could not be infinite after all. For a long stretch of history, nobody had the astronomical evidence needed to settle the question properly, only competing guesses about what an infinite star-filled universe should look like from the inside. The real resolution came only in the 20th century, once cosmologists had solid evidence that the universe has a finite age, having begun a finite number of billions of years ago, and has been expanding ever since. A finite age means light from the most distant stars and galaxies simply has not had time to reach Earth yet. No matter how large the universe eventually turns out to be, which alone breaks Ohlbers' assumption that every line of sight should already have caught up with a star. On top of that, the expansion of space stretches the light that has arrived from very distant, very old sources into longer wavelengths, shifting much of it out of the narrow band of light human eyes can actually detect, dimming it further still. A dark night sky, it turns out, is not an absence of anything. It is a direct, visible clue about the age and history of the entire universe, hiding quietly in plain sight between the stars. A household worried about the future decides to spend less and save more, a decision that looks purely responsible from the inside, the kind of caution any careful person would praise. But every dollar not spent by that household was, a moment earlier, income waiting to land in someone else's pocket. A shopkeeper, a waiter, a landlord. Multiply that single household's caution across an entire economy during a downturn, with millions of households pulling back at once, and businesses everywhere see revenue fall, respond by cutting jobs and wages, and the total income available across the economy shrinks. The very savings people were trying to protect end up smaller than if everyone had simply kept spending. The economist John Maynard Keynes developed this argument carefully during the 1930s while studying the Great Depression, though the germ of the idea had appeared 2 centuries earlier in a satirical poem by the Dutch writer Bernard Mandeville, who suggested that private thrift, however virtuous it looked, could be publicly ruinous. Keynes formalized the mechanism. Spending by one person becomes income for another, in a chain that runs through an entire economy. So a widespread pullback in spending does not just reduce consumption, it reduces the total income available to be saved from in the first place. The paradox is specifically a feature of collective timing during a downturn, not a claim that saving itself is bad. An individual household saving more in ordinary times does nothing to the wider economy at all, and remains exactly as sensible as it looks. The trouble arises only when a very large number of people cut back simultaneously, in response to the same shared fear, at a moment when total spending in the economy is already the thing propping up total income. What is prudent for any single household in isolation becomes destructive once enough households do it together at the same worried moment. The insight became a central argument for why governments, rather than tightening their own spending to match a frightened public, are often urged to do the opposite during a downturn, stepping in to spend precisely when everyone else has quietly decided to stop. A hungry donkey stands precisely midway between two piles of hay, identical down to the last wisp, equally fresh, equally close, equally appealing in every measurable way. A purely rational creature, the puzzle goes, would have no logical basis for choosing one pile over the other, since reason alone gives it nothing to break the tie. And a creature that only ever acts on a reason strong enough to justify the action would, absurdly, remain frozen between the two piles, unable to choose either one until it starved. The scenario carries the name of the 14th century French philosopher, Jean Buridan, who spent real effort studying questions of free will and moral choice. Though historians are fairly confident he never actually wrote the donkey version of the story himself. It appears to have been invented later, likely by critics summarizing and mocking a position closer to Buridan's genuine argument, that a rational will, faced with two options of exactly equal value, would need some further push to move at all. The donkey was a caricature of that argument, sharpened into a cleaner, funnier shape than anything Buridan himself put on paper. The puzzle is really a test of what reason alone can and cannot accomplish. If choosing always requires identifying a reason that favors one option over another, then a genuine tie between two options ought to be paralyzing, since there is nothing left to decide with. In practice, of course, no real donkey or person actually freezes this way when faced with two equally good sandwiches or two equally fine parking spots. People pick one anyway, quickly and without much agonizing, which suggests something in real decision-making does not wait around for a fully justified reason before acting, some small internal nudge, a passing preference, plain restlessness that resolves the tie without needing to explain itself. That gap between the donkey frozen by pure logic and the person who just picks a sandwich is exactly why the story has stuck around for centuries as a favorite way of showing why decision-making needs more than reason alone ever seems able to supply. A factory grades its workers on units produced per shift, and units produced climbs steadily, exactly as intended, right up until someone notices the quality of those units has quietly fallen. A call center grades its staff on average call length, and average call length drops, right up until customers start complaining that their actual problems never get solved, just rushed off the phone. In both cases, the numbers moved exactly the way management wanted. Whatever the numbers were originally supposed to represent moved in the opposite direction instead. The economist Charles Goodhart first stated the underlying principle in 1975 while studying British monetary policy, where a similar problem had emerged. Once regulators started explicitly targeting a particular measure of the money supply, that measure stopped reliably predicting the economic outcomes it had previously tracked well, simply because banks and markets adjusted their behavior around the new target. The insight generalized quickly, and the shorthand version now carries his name. When a measure becomes a target, it ceases to be a good measure. The logic underneath it is straightforward once it is pointed out. A number gets chosen as a proxy in the first place because it happens to correlate with something harder to measure directly: genuine productivity, real customer satisfaction, actual price stability. That correlation holds only as long as people are pursuing the underlying goal, and the number is simply riding along as a side effect. The instant people start pursuing the number itself, directly as the thing they are graded and rewarded on, They find every available shortcut that moves the number, without necessarily moving the real thing behind it. And the correlation that made the number useful quietly comes apart. Nearly every system built around a single visible metric carries this same seed inside it. Whether it is a school judged by standardized test scores, a hospital judged by wait times, or a social platform judged by time spent per user. None of this means metrics are useless, only that a target, once known and rewarded, changes the very behavior it was meant to passively describe. The map, chosen carefully to represent the territory, starts quietly redrawing the territory to match itself instead. Start with a heap of 10,000 grains of sand. Remove one grain. Still obviously a heap. Remove another. Still a heap. Every single step in this process follows the same undeniable rule. Taking away one grain from something that is clearly a heap cannot possibly turn it into something that is not a heap, since one grain is far too small a difference to matter. Repeat that step 10,000 times though, one grain at a time, following a rule that never once seemed false, and you end up with a single grain of sand sitting alone, which is obviously not a heap of anything. The puzzle takes its name from the Greek word for heap, and is generally credited to the philosopher Eubulides of Miletus in the 4th century before the Common Era. The same thinker behind the sentence, "This statement is false." What makes it a genuine paradox rather than a simple trick is that every individual step really does seem true on its own. Nobody can point to some specific grain, the 7,400th one removed, say, and claim that removing that particular grain was the one that finally broke the heap. And yet the starting heap and the ending single grain are clearly, obviously different. So somewhere along the way, something changed that the step-by-step rule insists never could have. The same fuzziness shows up constantly outside of sand. There is no single hair whose loss turns a full head of hair into baldness, and no single day that turns a child into an adult, and no single wavelength of light where red distinctly becomes orange. Yet baldness, adulthood, and orange are all real, meaningful categories that plainly do exist. Somewhere between one extreme and the other, a genuine change happens gradually, with no sharp boundary marking exactly where. Philosophers still argue over where the fault actually lies, whether it is a flaw in language, which uses words with edges too blurry for logic's sharp rules, a flaw in the logic itself, or simply a fact about the world, that some real categories were never going to have sharp lines in the first place, however much our reasoning wants to insist that they should. A talented salesperson closes deal after deal and is promoted into sales management as a reward. Managing a sales team, though, turns out to require a completely different set of skills. Coaching, delegating, resolving conflict, none of which the original promotion was actually testing for. The newly minted manager struggles and stays exactly there, since a struggling manager rarely gets promoted any further, and companies are, for obvious reasons, reluctant to demote someone back down. The educator Lawrence Peter proposed this pattern in a 1969 book, written partly as satire, but built around a genuinely sharp observation about how promotion decisions actually get made inside organizations. Competence in a current role is, almost everywhere, treated as the primary evidence that someone will also be competent in the next, harder role up the ladder, even when the two roles call for entirely different skills. Since promotions generally stop only once someone's performance stops impressing, and since impressive performance is exactly what got them promoted in the first place, employees tend to rise, layer by layer, right up to the specific level where the skills that carried them no longer apply, and then remain stuck there indefinitely, neither promoted further nor sent back down. For years, the idea was treated mostly as a wry observation rather than a documented fact, until economists studying detailed personnel records from real sales organizations found genuine statistical evidence behind it. Salespeople who were promoted into management based on strong individual sales numbers tended, on average, to become weaker managers than salespeople who were promoted based on other signals. Exactly the pattern Peter had described decades earlier as more or less a joke. Strong individual performance, it turned out, correlated poorly with strong leadership ability, and companies were promoting on the wrong signal anyway. The organization that emerges from years of this pattern ends up staffed, layer after layer, by people who were excellent at the job just below the one they currently hold, rather than the job they are actually doing now. A quiet, structural kind of mismatch that keeps rebuilding itself with every well-earned promotion. Mathematics, at the turn of the 20th century, rested on a foundation that felt almost too obvious to question. A set is simply any well-defined collection of things, and you can group together whatever objects you like, including, why not, other sets. In 1901, the philosopher and mathematician Bertrand Russell asked a deceptively small question about that foundation, and the whole thing cracked open. Take the set of all sets that do not contain themselves as a member. Most ordinary sets fit this description easily. The set of all cats is not itself a cat, so it does not contain itself, and belongs in this collection along with nearly everything else you could name. Now ask the obvious follow-up question. Does this particular set, the set of all sets that do not contain themselves, contain itself? If it does contain itself, then by its own defining rule it should not, since it is only supposed to hold sets that do not contain themselves. If it does not contain itself, then it fits its own defining rule perfectly, which means it should be included after all. Either answer immediately contradicts itself, and there is no third option to fall back on. Russell brought the contradiction to the attention of the German logician Gottlob Frege, who had just finished years of work building mathematics up from exactly this kind of naive set theory, and the timing could hardly have been worse. Frege's second major volume was already at the printer. He added a hurried note acknowledging that his entire foundation had just been shown to contain a genuine contradiction, a rare and painful moment of intellectual honesty in the history of mathematics. The fix took years of careful rebuilding. Mathematicians developed stricter, more limited rules for what counts as a legitimate set, rules specifically designed to block a collection from ever being allowed to reference itself the way Russell's paradox required. Modern set theory, the version underlying nearly all of contemporary mathematics, still carries the scars of that repair work, built from the ground up around a short question that for a few uncomfortable years had no answer that did not contradict itself. A steam engine redesigned to burn coal more efficiently should, common sense insists, mean less coal burned overall for the same amount of work. The economist William Stanley Jevons looked at the actual historical numbers for English coal consumption in 1865 and found the opposite had happened. As steam engines became steadily more efficient across the 19th century, total coal consumption kept climbing rather than falling, because the more efficient engines made coal power cheap enough to justify entirely new uses that would never have been worth the expense before. The mechanism behind the reversal is really about price and demand, rather than anything mysterious about coal specifically. Efficiency lowers the cost of getting a given amount of work done, and a lower cost for almost anything people want tends to increase how much of it they choose to use. If the efficiency gain is large enough, and the appetite for more of the underlying activity is strong enough, the resulting increase in total use can outpace and even overwhelm the savings the efficiency improvement was supposed to deliver in the first place. Jevons was not arguing that efficiency is worthless, only that it cannot be counted on by itself to reduce total consumption the way it seems like it obviously should. The same tension resurfaces in plenty of modern debates. More fuel-efficient cars can encourage longer commutes and more driving overall, since each mile costs less than it used to. Cheaper, more efficient LED lighting has, in some studies, led to more total light being used around homes and cities, simply because lighting became cheap enough to use more liberally. Even data storage follows a similar pattern, with more efficient, cheaper storage, inviting people to save far more than they ever would have bothered keeping at higher cost. None of this means efficiency is the wrong goal. It means efficiency alone, without some other limit on total demand, tends to be a weaker lever on total consumption than it looks like it should be. A quiet reminder that cheaper is rarely the same thing as less. Two encyclopedias, published around the same time, once reported two noticeably different lengths for the border between Spain and Portugal, a border that had not, of course, moved an inch between the two publications. The mathematician Louis Fry Richardson went looking for an explanation in the 1950s and found something stranger than a simple printing error. The length of a border, or a coastline, genuinely depends on the length of the measuring stick used to walk along it, and gets systematically longer without any obvious limit the smaller that measuring stick becomes. A coastline is jagged at almost every scale you look at it, from broad bays down to small inlets, down to individual rocks and grains of sand. A long ruler, laid end to end along the coast, cuts straight across small inlets and outcrops it is too coarse to follow, missing that extra distance entirely. A shorter ruler catches those same inlets, adding real length the longer ruler had simply skipped over. Shrink the ruler further still, down toward the scale of individual rocks, and it keeps finding yet more jagged detail to trace, and the measured length keeps climbing, with no obvious point where it settles down to one true, final number. The mathematician Benoit Mandelbrot built on Richardson's observation in a landmark 1967 paper, using the Coastline puzzle to help introduce the idea of a fractal, a shape that keeps showing roughly the same kind of roughness and detail no matter how far you zoom in on it. Coastlines, mountain ranges, river networks, and the branching patterns of lungs and trees all show this same self-similar jaggedness at multiple scales, which is part of why a simple single number for their length turns out to be less a fixed physical fact and more a choice about how closely you have decided to look. A country's coastline, printed confidently in an atlas as a single tidy figure, is in truth an answer that depends entirely on the question you asked it, and a slightly different ruler would have given you a slightly, or not so slightly, different coastline entirely. Ask most people to compare their own number of friends to the average number of friends their own friends have, and something a little deflating turns out to be true almost across the board. On average, your friends have more friends than you do. This is not a comment on anyone's personality or popularity. It is true for nearly everyone in a typical social network, including plenty of people who are, by any reasonable measure, quite well liked. The sociologist Scott Feld proved the effect mathematically in 1991, and the explanation, once you see it, has nothing to do with charm or likability at all. It is a simple, if slightly sneaky, consequence of how averages get sampled inside a network of friendships. A person with an unusually large number of friends shows up on an unusually large number of other people's friend lists simply because they have so many connections. A person with very few friends shows up on very few lists. When you calculate the average number of friends your own friends have, you are, without realizing it, oversampling exactly the well-connected people, since they appear disproportionately often as somebody's friend, and undersampling the loosely connected ones. The math pulls the average up past what any individual, typical person actually has. The same underlying sampling effect turns out to be useful well beyond a minor blow to anyone's self-esteem. Epidemiologists have used a version of it to track the spread of contagious disease through a population, since asking a random group of people to name a friend, rather than studying the random people directly, tends to identify more highly connected individuals. The very people a fast-spreading disease is statistically more likely to reach early. Researchers have used the same logic to try to detect emerging social trends earlier than ordinary random sampling would catch them, following the friends of a random sample rather than the sample itself. The paradox holds precisely because popularity in a network is never evenly spread out. A small number of highly connected people quietly drag the average up for everyone standing near them, a strange mathematical kind of company to be keeping without ever noticing it. An open society prides itself on tolerating a wide range of beliefs, arguments, and ways of living, resolving its disagreements through debate rather than force. But suppose one of the ideas competing for space inside that open society is a movement that rejects debate entirely, one that plans, quite openly, to seize power and eliminate the very tolerance that gave it room to grow in the first place. Extend that movement the same unlimited tolerance offered to every other idea, and the open society has, in effect, handed its own destroyer a peaceful, protected route straight to the door. The philosopher Karl Popper laid out this argument in 1945, in the middle of writing about the intellectual roots of totalitarianism, reasoning through what he called the paradox of tolerance. A society that insists on tolerating absolutely everything without exception cannot actually guarantee its own survival as a tolerant society, because tolerance offers no built-in defense against a movement that intends to use that same tolerance as a weapon against it. Popper's conclusion was not a call for unlimited suppression of disagreeable ideas, a position he explicitly rejected as its own kind of danger. He argued instead for a narrow, carefully bounded exception. A tolerant society has the right, and arguably the obligation, to refuse tolerance specifically to movements that reject rational argument outright and rely instead on suppression, intimidation, or violence as their actual method. Popper was careful about where he drew that line, warning that the exception should never be stretched to cover mere disagreement, unpopular opinions, or ideas that are simply offensive, rather than genuinely aimed at ending open debate itself. Applied too broadly, the same reasoning meant to protect tolerance can become an excuse for silencing anyone a majority found inconvenient, which would defeat the entire purpose just as thoroughly as unlimited tolerance would. The argument has remained a recurring reference point ever since, in debates over free expression, extremism, and where exactly the edges of an open society's patience ought to sit, precisely because Popper never offered a simple formula, only a difficult, permanently unfinished line to keep redrawing. Two envelopes sit on a table. One contains exactly twice as much money as the other, though you do not know which is which, and you are handed one of them at random. Before you open it, you are offered the chance to swap for the other envelope instead. A quick calculation seems to argue strongly in favor of swapping. Whatever amount is in your envelope, call it a certain sum, there is an equal chance the other envelope holds either half that sum or double it. And averaging those two possibilities out gives an expected value higher than what you are currently holding. So you should switch. But the exact same reasoning applies again the instant you do switch, recommending you switch right back, and then again after that, forever, in a circle that never settles anywhere. The puzzle circulated among mathematicians for decades in various forms, before settling into roughly its current shape. Whatever the correct resolution turns out to be, one thing is obvious without needing any advanced mathematics at all. No sound reasoning could possibly recommend switching envelopes in an endless loop, since both envelopes are sitting right there, sealed, with two specific fixed amounts of money already inside them, before you ever touched either one. Something in the calculation has to be quietly broken, even though every individual step in it looks, on the surface, perfectly reasonable. The most widely accepted resolution points to a subtle error in how the calculation treats the unknown amount. The step that says the other envelope holds either half or double your amount, each with equal chance, secretly assumes something odd, that whatever specific number happens to be in your hand, the other envelope's relationship to every possible number is symmetric in a way that is not actually true once you account for the fact that both amounts were fixed together, as a pair, before the envelopes were ever handed out. Treating your own envelope's amount as some open, unknown variable, rather than one half of an already fixed pair, is what quietly smuggles the contradiction into what looked like ordinary probability. Mathematicians still debate the cleanest, most rigorous way to state exactly where the error creeps in, even though virtually everyone agrees, well before working out the details, that an error is hiding in there somewhere. Here is a coin flip game. A coin is tossed repeatedly until it lands tails for the first time. If it takes just one flip, you win $2. If it takes two flips, you win $4. Every additional flip before the first tails doubles the payout again. 4 flips wins $16, 10 flips wins over $1,000, and so on without any upper limit at all. Work out the mathematically correct average payout of this game, weighting every possible outcome by its exact probability, and the answer comes out infinite. By that logic, a rational player should be willing to pay any finite amount of money, no matter how large, just for the chance to play. In practice, offered the exact same game, almost nobody will pay more than a handful of dollars to take part. The mathematician Daniel Bernoulli examined the puzzle carefully in 1738, after his cousin Nicolas first posed a version of it to their circle of fellow mathematicians. The gap between the infinite mathematical average and everyone's modest real-world willingness to pay demanded some kind of explanation. Since nobody involved seemed to be behaving irrationally exactly, they just consistently refused to treat the two figures as equally meaningful. The enormous payouts that make the mathematical average so large are also exquisitely rare, and most actual games end after just 1 or 2 flips, for a small and unremarkable prize. Bernoulli's proposed resolution reshaped how economists have thought about money and value ever since. He argued that people do not actually value raw quantities of money in a straight line, dollar for dollar. Instead, each additional dollar tends to matter a little less than the one before it, especially once basic needs are comfortably covered, an idea now generally called diminishing marginal utility. Under that more realistic way of valuing money, the astronomically rare, astronomically large payouts stop dominating the calculation the way they do under simple raw averaging, and the modest, sensible price people are actually willing to pay for the game turns out to make perfect sense after all. A single coin, flipped over and over, ended up teaching economics one of its oldest and most durable lessons, that a number on paper and a number that actually feels meaningful to a person are not always the same thing. A city spends heavily reinforcing its flood defenses ahead of a storm season that, in the end, produces no serious flooding at all. A public health campaign vaccinates a population against a disease that, thanks largely to the vaccination itself, never turns into a serious outbreak. In both cases, success looks, from the outside, indistinguishable from an overreaction to a threat that was probably never that serious to begin with. The prevention worked exactly as intended, and that very success is what erases the evidence that it was ever needed. Public health researchers and safety engineers have documented this pattern across a wide range of fields, sometimes calling it the prevention paradox or the preparedness paradox. The clearest large-scale example many people lived through directly was the extensive remediation work carried out in the years leading up to the year 2000, when programmers around the world rewrote enormous amounts of old software that stored years using only 2 digits, out of concern that computer systems would misread the year 2000 as 1900 and fail in unpredictable ways. The remediation effort succeeded. Disruptions on New Year's Day were minor and scattered, and within a few years plenty of people had concluded that the entire concern had been an overblown panic in the first place, since nothing serious appeared to happen. The underlying logic problem is genuinely hard to escape. A disaster that is fully prevented produces no visible wreckage, no counterfactual footage of what would have happened, nothing tangible for anyone to point to later as proof the spending was justified. A disaster that happens despite prevention efforts, or one that prevention only partly blunts, leaves behind exactly the kind of visible damage that makes the next round of spending easy to justify. Prevention, judged purely by what people can see afterward, tends to look most wasteful exactly when it has worked best. Nobody has found a clean fix for the incentive problem this creates. Governments and institutions still tend to fund prevention more generously right after a visible disaster than in the quiet years when prevention is actually working. 2 identical jars sit side by side, each filled with 100 colored balls. The first jar, you are told plainly, holds exactly 50 red balls and 50 black ones. The second jar holds some unknown mixture of red and black, in proportions nobody will tell you. Offered a bet on drawing a red ball from either jar, most people, given a free choice, pick the first jar, the one with clearly known odds, even when the payout offered is identical either way. Ask them to bet on black instead, and most people still pick the first jar. Both preferences together do not actually make logical sense, since if the unknown jar's mixture is worse for red, it should, on average, be correspondingly better for black, and a purely rational gambler with no other information should be roughly indifferent between the 2 jars either way. The economist Daniel Ellsberg, later far more famous for a very different act involving leaked government documents, ran exactly this experiment in 1961 to expose a real gap in how economists at the time modeled decisions made under uncertainty. Standard theory treated known risk, where the odds are stated plainly, and pure ambiguity, where the odds are simply unknown, as functionally interchangeable so long as the underlying probabilities worked out the same on average. Ellsberg's subjects, again and again, revealed a real and consistent preference for known risk over unknown ambiguity, a preference that could not be explained away as ordinary caution about bad odds, since nothing about the actual numbers favored the known jar over the hidden one. Economists now treat this pattern, ambiguity aversion, as a genuine and separate force from ordinary risk aversion, one driven less by the odds themselves and more by a felt lack of control over odds that cannot be verified or checked. The preference shapes real decisions well outside the laboratory, from why investors often favor familiar, well-understood assets over unfamiliar ones with comparable expected returns, to why insurance against a poorly understood risk tends to command a noticeably higher premium than insurance against an equally likely but better understood one. People, it turns out, are willing to pay a real price just for the comfort of knowing the odds, whatever those odds happen to actually be. Offered a straightforward choice between a guaranteed prize and a gamble with a slightly higher average payout, but some chance of winning nothing, most people take the sure thing, which seems like ordinary, sensible caution. Now, take that exact same gamble shrink the certainty in both options by an identical small amount, so the guaranteed prize becomes merely very likely rather than certain, and the same people often flip their preference entirely, choosing the once avoided gamble now that both sides carry some risk. Standard rational choice theory says that shared equal shrinkage should not change anyone's preference at all, since the same proportional gamble was just added to both sides equally. People's actual answers say otherwise. The economist Maurice Allais devised the experiment in 1953, presenting a pair of carefully matched choices designed to expose exactly this inconsistency in how economists at the time modeled rational decision-making. The leading theory of the era treated a probability as simply another number to be weighed in a straightforward calculation. 100% certainty counted for exactly as much, proportionally, as 99% likelihood, with no special extra weight attached to true certainty itself. Allais's subjects behaved as if certainty carried a bonus all its own, something the clean mathematics of the leading theory had no room for. The finding mattered well beyond a clever party trick, since it directly challenged the dominant economic model of rational choice at the time, one built on the assumption that people simply calculate expected outcomes and pick the higher one. Allais's results suggested something more specific was going on. People do not treat a drop from certainty to near certainty the same way they treat an equally sized drop, somewhere in the middle of the probability scale, a distortion concentrated right around the edges of sure and impossible. The finding helped motivate a very different model of decision-making, developed decades later by the psychologists Daniel Kahneman and Amos Tversky, and eventually recognized with a Nobel Memorial Prize in economics, one built specifically around how people actually weigh gains, losses, and the special psychological pull of certainty, rather than around how a purely rational calculator, uninterested in the comfort of a sure thing. A company built around one sharp, winning idea rides that idea to real dominance in its market. And the temptation, once the winning formula is obvious to everyone, is to lean into it even harder. More of what worked, sharper focus on the original strength, less time spent on the scattered experiments and outside listening that produced the breakthrough in the first place. For a while this works beautifully, and the company grows more confident with every quarter that confirms the formula was right. Then the market shifts. In some way the old formula was never built to handle, and the very discipline that made the company great turns out to have made it brittle in exactly the same motion. The business scholar Danny Miller named this pattern in a 1990 book, borrowing the Greek myth of Icarus, the young man given wings of feathers and wax who flew so confidently and so high that the sun melted the wax holding his wings together. Miller studied dozens of once dominant companies across different industries and found a strikingly consistent shape underneath their eventual declines. It was rarely a sudden outside disruption that caught them by surprise. It was a slow, self-inflicted rigidity, built directly and gradually out of whatever specific strength had made them successful in the first place. Whether that was operational efficiency, a beloved product line, or an aggressive growth strategy, pushed harder and harder until it stopped bending to a changing market at all. Confidence, in Miller's account, is the quiet engine of the whole pattern. Early success is real evidence that a strategy works, and it is entirely reasonable to lean into evidence that keeps confirming itself. But that same confidence gradually crowds out the doubt, the outside perspective, and the willingness to experiment that had actually produced the original success, replacing genuine judgment with something closer to habit. The company does not stop trying. It keeps trying exactly as hard as before, at exactly the thing that used to work. Icarus never doubted his wings until the moment they failed him, and by Miller's account, neither do most companies, right up until the strength they trusted most turns out to be the very thing they can no longer put down. It seems like professional sports, filled with the most highly trained athletes on earth, should be the last place where luck decides very much of anything. The investment analyst Michael Mauboussin, studying decades of statistics across a range of professional sports, found something close to the opposite. As competitors within a field get better and more evenly matched over time, the role luck plays in deciding any single contest actually grows, not shrinks. The mechanism becomes clear once you separate the two things sitting inside every match's final score. The underlying skill gap between the two sides, and the ordinary randomness, a bad bounce, a questionable officiating call, a gust of wind. that no amount of skill can fully cancel out. Early in a sport's history, or in a lopsided matchup between a strong team and a weak one, skill differences are often large enough to swamp the randomness almost entirely, and the better side wins reliably, but push every competitor's skill up toward the highest achievable level, the way decades of professional training, coaching, and equipment improvements tend to do across an entire sport. And the skill gap between any two elite competitors shrinks toward nearly nothing. Once that gap is small enough, the ordinary randomness that was always present but previously drowned out becomes the larger of the two remaining factors in who actually wins. Mobusen used the finding to build a rough scale across different sports and industries, measuring how much of the variation in outcomes traces back to skill versus luck, and found real measurable differences. Some competitive activities lean heavily on skill, others surprisingly heavily on chance, and the ratio shifts, predictably, as any given field matures. The same logic reaches beyond sports entirely, into investing and business strategy, and any field where the most capable competitors have converged toward a similarly high level of ability. Judging a single result, one winning quarter, one championship, purely on its outcome becomes less reliable exactly as a field's average skill rises, since a bigger share of any single result is by then luck standing in for a skill gap that barely exists anymore. The most skilled era in a sport's history, oddly enough, may also be the era in which any single dame tells you the least about who was actually better. A modern aircraft cockpit automates the overwhelming majority of ordinary flight, holding altitude, adjusting for wind, managing fuel, tasks a human pilot once handled by hand for an entire career. The automation is good at this, consistently better than a tired human across a long, routine flight. But automating away the routine work leaves the human pilot with less and less practice actually flying the plane, exactly at the moment that the only situations left requiring a human are the rare, difficult ones the automation itself was never designed to handle. The engineering psychologist Lisanne Bainbridge described this exact tension in an influential 1983 paper examining cockpit automation, naming it the irony of automation. Handing routine tasks to a machine is meant to reduce the burden on a human operator and reduce the odds of ordinary human error. It does both of those things quite reliably, but the operator's skill at the tasks now being automated does not simply sit in reserve, ready and sharp, waiting to be called on. Like any skill, it fades from disuse, and it fades precisely while it is being used less and less, right up until the rare moment something goes wrong outside the automation's design assumptions, and the system suddenly needs a sharp, well-practiced human to take over immediately. Exactly the kind of practice the automation has been quietly eroding all along. Bainbridge's original study focused on aviation, but the same tension has since shown up in field after field that leans on automation for its routine work. Doctors relying heavily on diagnostic software can find their own independent diagnostic instincts duller than a less automated colleague's, right up until a case slicks past the software's assumptions. Drivers using increasingly capable driver assistance systems can grow less practiced at the exact split-second judgment calls those systems occasionally fail to make correctly. In each case, automation does not remove the need for human skill, so much as concentrate that need into a smaller, harder, rarer set of moments, ones that demand more from an operator who has had fewer and fewer chances to stay sharp. The safest system on paper ends up depending most heavily on a kind of human expertise that the system's own convenience keeps quietly wearing away. A dollar bill goes up for auction with one unusual rule attached. The highest bidder wins the dollar, as expected, but the second highest bidder also has to pay whatever they bid and gets nothing at all in return. Bidding usually opens small and sensible, 5 cents, 10 cents, a genuine bargain either way. But once two bidders find themselves near the top, each one faces an ugly private calculation. Bid higher, and you might still come out ahead, or at least break even if you win. Stop bidding now, and you lock in a guaranteed loss on whatever you have already bid, with nothing at all to show for it. That second option looks so much worse than the first that both bidders keep raising, past 50 cents, past $1, sometimes far past it, each one trying to avoid a guaranteed loss by risking a larger one. The economist Martin Shubik designed the game in 1971 as a classroom demonstration of a psychological trap called escalating commitment. The auction reliably produces the same absurd result: a single dollar bill selling between two increasingly desperate bidders for well more than $1, sometimes many times over, with the loser walking away having paid real money for absolutely nothing. Neither bidder behaved irrationally at any single step along the way. Each decision to raise the bid one more increment, viewed on its own, made a kind of narrow sense given what had already been spent. It is the accumulation of many individually defensible small decisions that produces a wildly indefensible final outcome. The same trap operates well outside classroom demonstrations. Nations have kept fighting costly wars years after the original goals stopped making any sense, largely to avoid admitting that everything already spent achieved nothing. Companies have kept funding failing projects, throwing good money after bad, specifically because so much has already been invested that stopping feels like the greater loss. Economists call this general pattern the sunk cost trap, the tendency to let money or effort already spent and permanently unrecoverable either way distort a decision that should really only be about what happens from this point forward. The dollar bill sold at auction was never really the point of the game. The actual prize every time was watching two reasonable people talk themselves into paying far more than anything was ever worth. A person collapses in a crowded public space in clear need of help. Simple intuition suggests that more witnesses should mean better odds of getting that help, more eyes to notice the emergency, and more hands available to respond. Careful experiments have found close to the opposite. The more bystanders present, the less likely any single person in distress is to actually receive help, and the longer it typically takes for anyone to step in when help does eventually come. The psychologists John Darley and Bib Lotune demonstrated the effect through a series of staged emergency experiments in the late 1960s, placing research participants in situations: a room filling with smoke, a staged medical emergency heard over an intercom, and quietly varying how many other people the participant believed were also present and aware of the situation. Participants who believed they were the only witness intervened quickly and reliably, nearly every time. Participants who believed several other people were also aware of the same emergency intervened far less often, and far more slowly when they did intervene at all. Two overlapping mechanisms explain the pattern. The first, called diffusion of responsibility, means that as the number of witnesses grows, the personal sense of individual obligation to act gets spread thinner across the whole group, and no single person feels as fully on the hook as a lone witness would. The second is a kind of social reading of the room. Since nobody wants to overreact to a false alarm in front of others, each bystander glances around, sees everyone else calmly not reacting yet, and quietly concludes the situation may be less urgent than it looks, even while everyone else in the group is doing exactly the same private calculation and reaching the exact same mistaken conclusion. Understanding the mechanism has turned out to be one of the more practical findings in the whole discipline. Safety training now often teaches bystanders to break the pattern directly by pointing at a specific person and assigning them a specific task, since naming an individual collapses the diffusion the crowd was otherwise relying on to stay comfortably still. A country discovers a vast deposit of oil beneath its soil, or diamonds, or some other valuable natural resource. And the discovery ought to be nothing but good news, a straightforward path to national wealth. Economists studying the actual outcomes across many resource-rich countries over recent decades found something considerably more troubling. Nations with the richest natural resource endowments have often grown more slowly, developed less stable institutions, and stayed poorer on average than comparable nations with far fewer resources to draw on at all. Economists began documenting this pattern closely in the 1990s and identified a few overlapping mechanisms behind it. A resource boom tends to push up the value of a country's currency, since foreign buyers need that currency to purchase the resource. And a stronger currency makes everything else the country produces, manufactured goods, agricultural exports, more expensive and less competitive on the world market, a dynamic economists sometimes call Dutch disease, after a similar episode that hit manufacturing in the Netherlands following a large natural gas discovery. Industries outside the resource sector wither for lack of competitiveness. leaving the whole economy dangerously dependent on a single commodity whose price can swing wildly from year to year. The second mechanism runs through politics rather than pure economics. A hugely valuable resource concentrated in one place creates an enormous capturable prize, and capturing control of that prize through corruption, patronage, or outright armed conflict can become more lucrative than the harder, slower work of building broad, diversified economic institutions that serve the wider population. Several of the countries hit hardest by the pattern have also suffered civil conflicts, fought substantially over control of the resource wealth itself, rather than over any of the usual grievances. Not every resource-rich country has fallen into this trap. A handful of nations that had already built strong, accountable institutions before their resource boom hit have managed the wealth well, investing it broadly rather than letting it concentrate and corrode. The pattern, though consistent enough across many countries for economists to treat it as a real structural risk, has never been an unbreakable rule, only a warning about how easily sudden wealth can undermine the very foundations meant to manage it. Set out deliberately to become happier, checking in regularly on how well the project is going, and something about the checking itself tends to get in the way. People who report chasing happiness as an explicit, ongoing goal often describe feeling less happy than people who never frame their life that way at all, pursuing instead some other absorbing goal, a piece of work, a relationship, a skill worth mastering, and finding, almost as an afterthought, that they would become happy somewhere along the way without ever quite aiming for it directly. The philosopher Henry Sidgwick outlined the underlying shape of this idea in the 19th century, noting that pleasure seems to arrive most reliably as a side effect of genuine absorption in something outside itself, rather than as a direct target that can simply be pursued head-on the way a person pursues a promotion or a degree. Chase happiness explicitly enough, and ordinary moments start to feel less like living and more like a performance review, with some quiet internal voice constantly checking whether the moment currently qualifies as happy enough. A habit that tends to pull a person straight out of the moment it is supposedly evaluating. Modern well-being researchers, working with considerably more data than Sidgwick ever had available, have circled back to something remarkably close to his original observation. Measures of engagement, the sense of being genuinely absorbed in a task that stretches a person's abilities, and measures of meaning, the sense that one's efforts connect to something larger than oneself, both track more closely with people's overall reported life satisfaction than direct measures of how much pleasant feeling someone is chasing in any given moment. A person deeply absorbed in solving a hard, interesting problem often reports very little conscious happiness in the moment itself, and yet rates their overall life as considerably more satisfying than a person actively working to feel pleasant sensations on demand. None of this is really an argument against enjoying pleasant things, only a description of a strange asymmetry in how happiness seems to work. Aimed at directly, it tends to slip away, and pursued indirectly as the quiet byproduct of some other absorbing goal, it has a much better habit of actually showing up. Scoop up a single liter of ordinary open seawater, seemingly one of the most uniform environments on the planet. No rocks to hide behind, no separate rooms, no obvious boundaries at all. And examine it under a microscope. It can easily hold dozens of distinct species of plankton, all competing directly for the exact same limited handful of nutrients and the exact same sunlight filtering down from above. According to one of ecology's oldest and most well-supported principles, that should not be possible. The principle in question, sometimes called the competitive exclusion principle, holds that when two species compete for genuinely identical resources within a stable, unchanging environment, one of them will eventually outcompete the other so completely that the loser disappears from that environment altogether, since any tiny edge, compounded generation after generation, should eventually become an overwhelming one. Open water looks like about as stable and uniform an environment as nature has to offer, with no obvious hiding places or specialized niches where a weaker competitor might find refuge from a stronger one. And yet it routinely hosts a stunning diversity of coexisting plankton species rather than the small handful the principle would predict. The ecologist G. Evelyn Hutchinson named this puzzle directly in a 1961 paper, calling it the paradox of the plankton, and it has remained one of ecology's most stubborn open questions ever since. Several explanations have been proposed, none of them fully settling the matter on their own. Ocean conditions may never actually hold still long enough for any one species to lock in a permanent advantage, with shifting temperature, light, and nutrient levels constantly resetting which species happens to have the edge at any given moment. Tiny, patchy variations in the water, at scales too small for researchers to easily measure, may also be quietly carving out small, temporary niches that a microscope studying bulk water samples simply cannot detect. More than 60 years after Hutchinson first named it, the paradox remains a genuinely open question, a reminder that one of ecology's cleanest, most confidently stated rules runs straight into an exception hiding in plain sight in a glass of ordinary seawater from any beach on Earth. Take a simple curve, one that swoops down and gets closer and closer to a straight line without ever quite touching it, and spin it around that line to form a solid shape, a long, narrowy horn stretching out toward infinity. The mathematician Evangelista Torricelli worked out the mathematics of exactly this shape in the 17th century, and found something that seemed at first look like it had to be a mistake. The horn's surface stretches on forever, genuinely infinite in area, since it keeps narrowing endlessly without ever quite reaching zero width. And yet the volume enclosed inside that same endless horn adds up, by ordinary calculus, to a single fixed, perfectly finite number. The shape later picked up the name Gabriel's horn, a nod to the archangel whose horn in religious tradition was said to sound at the end of the world, itself its own kind of infinite, world-ending event. The mathematics behind the paradox, once you sit with it, is not actually contradictory, even though it feels that way at first. Volume and surface area simply do not have to grow at the same rate as a shape stretches toward infinity. The horn narrows quickly enough, the further out you go, that the amount of new volume being added with each additional stretch of length shrinks fast enough to add up to a finite total, while the amount of new surface being added shrinks more slowly, not fast enough to ever stop accumulating. Mathematicians and students have enjoyed restating the result with a wink ever since. The horn could, in principle, be filled completely with a finite amount of paint, since its volume is finite, and yet that exact same finite amount of paint would never be enough to coat its own infinite outer surface, since that surface never stops growing. The joke captures something the equations, however correct, do not quite convey on their own. A single object holding two different kinds of infinity and finiteness at once, folded together into one continuous, narrowing shape. Torricelli's horn has never needed to exist as a physical object, to unsettle anyone who works through it properly. The mathematics alone does that on its own. Some numbers are obviously interesting. 0 is the origin of the whole number line. 7 is prime, and shows up constantly in puzzles and superstitions. A number like 1729 has its own small claim to fame, as the smallest number expressible as the sum of two cubes in two different ways. Other numbers seem, at least at first glance, to have nothing at all going for them, ordinary and forgettable. So here is a small, playful proof that this second group, the boring numbers, is actually empty. Suppose, for the sake of argument, that some numbers really are interesting and the rest really are boring. The boring numbers, whatever they turn out to be, form some group, and any group of whole numbers has to have a smallest member somewhere in it, since whole numbers cannot shrink forever without hitting a bottom. Call that number the smallest boring number. But hold on, being the smallest member of an entire category, distinguished from every other number in that category by that very fact, is itself a genuinely noteworthy, interesting property, which means the smallest boring number is not boring after all. It is interesting, specifically because it is the smallest boring one. So it does not actually belong in the boring pile. Remove it, and the exact same argument applies immediately to whatever new number is now the smallest one left in the boring group, and the one after that, and so on, with every candidate getting disqualified the instant it is singled out. The proof is not meant to be taken as a rigorous mathematical theorem, and mathematicians who tell it know perfectly well it is playing a bit loose with what interesting actually means, treating it cheekily as if it were a precise, well-defined mathematical property, rather than a vague human judgment. That looseness is really the whole point. The puzzle is a light-hearted illustration of how self-reference, a category defined partly by pointing back at its own members, can quietly unravel a distinction that seemed perfectly sound at first glance. Mathematicians have used it for generations as a gentle warm-up, a small, funny taste of the far more serious self-referential trouble that shows up later in logic and the foundations of mathematics, dressed up here as nothing more than a joke about boring numbers. Three friends are trying to decide where to eat, ranking 3 restaurants. Call them A, B, and C, according to their own personal preferences. Each friend's individual ranking is perfectly sensible and internally consistent, no contradictions at all inside any single person's list. And yet, when their preferences are combined and compared 2 at a time, something strange emerges. A majority of the group prefers restaurant A over restaurant B. A majority prefers B over C. By ordinary logic, that should settle it. The group should prefer A over C as well. Instead, a majority of the very same group prefers C over A, completing a loop with no clear winner anywhere in it, even though not one individual friend's own preferences were ever inconsistent. The mathematician and philosopher Marquis de Condorcet described this exact effect in 1785, while working through the mathematics of how voting systems combine many individual, perfectly rational preferences into a single collective decision. The contradiction he uncovered exists only at the level of the group, never inside any one voter's own head, which is part of what makes it so unsettling. There is no confused or irrational voter to blame anywhere in the room, only an aggregation process that can produce a cycle out of preferences that were each, on their own, entirely sound. The problem turned out to run far deeper than one unlucky example. The economist Kenneth Arrow proved, in a result that helped earn him a share of a Nobel Memorial Prize in economics roughly a century and a half later, that no possible voting system built from ranked preferences can fully guarantee avoiding this kind of cyclical inconsistency, while also satisfying a short list of otherwise entirely reasonable fairness conditions. Things like no single voter having outsized dictatorial power, and the system responding sensibly when voters' preferences shift. Every real voting system in actual use today, from simple plurality voting to more elaborate ranked systems, is really a series of practical compromises about which specific flaw a society has decided it can live with. Since Arrow's proof closed off the possibility of a system with no flaws to choose between at all. Nothing matters more to staying alive than water. No person can survive more than a few days without it, and entire civilizations have risen and collapsed around access to a reliable supply of it. A diamond, by contrast, serves no survival purpose at all, purely decorative, entirely unnecessary to anyone's continued existence. And yet water sells for pennies, while diamonds sell for a small fortune, an arrangement that seems on the face of it to have the priorities of the entire market exactly backward. Economists including Adam Smith wrote about this exact puzzle in the 18th century, puzzling over why something so plainly essential could be priced so far below something so plainly unnecessary. Smith himself did not fully resolve the puzzle in his own writing, though he was among the first to lay it out clearly as a genuine problem worth solving, rather than simply an odd curiosity. The resolution came later, once economists developed the idea of value at the margin, meaning the value of one additional unit of something, rather than the value of the entire category taken all at once. Nobody prices water by asking how important water is to human survival in general. A buyer prices the next glass of water specifically, and in most places water is abundant enough that one more glass of it, for a person who already has ready access to plenty, is barely worth anything at all, since it solves no real scarcity for them. A diamond, meanwhile, stays valuable precisely because diamonds have never become similarly abundant. One more diamond remains rare and desirable, adding real scarce value to whoever acquires it, in a way one more glass of already abundant water simply cannot match. Drop a person into a genuine desert far from any water source, and the relative prices flip entirely, with water suddenly worth vastly more than any diamond, exactly what the marginal explanation predicts, and the older, simpler explanation never could. Price, it turns out, was never really tracking how essential something is to survival in the first place. It tracks scarcity at the edge, one more unit at a time, which is precisely why the most essential thing in the world can still be the cheapest one on the shelf. Two particles interact briefly, then travel off in entirely different directions, eventually separated by an enormous distance. One on Earth, one, in principle, on the far side of the galaxy. Under a phenomenon quantum physics calls entanglement, measuring a property of one of those particles can instantly determine the corresponding property of the other, no matter how far apart they have drifted and with no delay at all. Faster, it seems, than any signal could possibly travel between them, even at the speed of light. The physicists Albert Einstein, Boris Podolsky, and Nathan Rosen described this exact scenario in a 1935 paper. Though they did not intend it as an endorsement, they meant it as a pointed criticism of quantum theory itself, arguing that a genuine instantaneous influence connecting two distant particles was so strange and violated the speed limits built into Einstein's own theory of relativity so directly that it had to reveal quantum theory was leaving something out, some hidden, more complete description of reality that would resolve the strangeness once discovered. Einstein called the apparent effect spooky action at a distance, a phrase that has stuck to entanglement ever since. The disagreement stayed a matter of pure interpretation, with no way to test it directly, until the physicist John Bell worked out a mathematical way to actually distinguish between Einstein's hidden, more complete explanation and quantum theory's own stranger account in a landmark 1964 paper. Real experiments testing Bell's proposed distinction, refined and repeated with steadily improving precision over the following decades, have consistently come down on quantum theory's side, confirming that entangled particles really do behave exactly the strange way the theory predicts, and ruling out the kind of hidden, ordinary explanation Einstein had hoped would eventually be found. Importantly, nothing about entanglement actually allows a usable message to be sent faster than light, since the outcome of any single measurement looks like pure randomness until it is compared against the distant partner's result, a comparison that still has to travel by ordinary means. What remains once the loophole for faster-than-light communication is closed off is simply a real, deeply strange connection between two particles, one that has survived some of the most careful experimental scrutiny in the entire history of physics. Suppose an inventor, struggling for years over a design that refuses to come together, is visited one evening by an older stranger who hands over the completed blueprints and disappears without explanation. The inventor builds the device exactly as shown, and it works. Decades later, that same inventor, now old, obtains a working time machine and finds themselves drawn back to that same struggling evening years earlier, driven by some private sense of unfinished business. They hand a younger version of themselves the very blueprints they were originally given. The idea has now traveled in a perfect loop, from the older inventor back to the younger one, with no point anywhere in the circle where it was actually invented by anybody at all. The scenario, and others shaped like it, draw their name from the old expression about pulling oneself up by one's own bootstraps. Since the information here seems to arrive from nowhere, looping endlessly, and causing itself with no beginning anywhere along the circle. It differs in an important way from the grandfather paradox, where a traveler's actions directly contradict and undo the very cause of the trip itself. Nothing here contradicts anything. Every single event in the loop is fully consistent with everything before and after it. The blueprints exist, the device gets built, the older inventor really does travel back, and really does hand over the blueprints. The loop holds together perfectly. It just never explains where the actual idea, the genuine moment of invention, originally came from. Physicists who study the mathematics of time travel within Einstein's general relativity refer to loops like this one as closed time-like curves, and the equations, worked through carefully, technically permit self-consistent loops of exactly this shape without producing any outright contradiction. Nobody has ever demonstrated a real object or event that plausibly requires such a loop to exist, and most physicists suspect closed time-like curves, even if mathematically permitted somewhere in the equations, may simply never occur in the actual physical universe. The bootstrap paradox remains a favorite of physicists and storytellers alike for exactly this reason. It breaks nothing in the strict logical sense the grandfather paradox breaks, and unsettles precisely by refusing to, insisting quietly that some things, in a universe built this way, might never need to have come from anywhere at all. A reader picks up a novel, knowing it will end in heartbreak, or buys a ticket to a film specifically because reviews promise it will be devastating, and comes away afterward calling the experience, without any apparent irony, a good time. Outside of fiction, people go to real lengths to avoid grief, fear, and heartbreak whenever they can. Inside fiction, those same emotions are often the entire draw, sought out deliberately, paid for in advance, and remembered fondly. Philosophers have circled this puzzle since at least ancient Greece, where Aristotle wrote about tragedy and proposed that watching stage suffering produces a kind of catharsis, a purifying release of pent-up pity and fear that leaves the audience emotionally lighter rather than more burdened, precisely because the suffering belongs to someone else, a character, and not to the audience member directly. Aristotle's specific explanation has been debated and revised many times since, but the underlying question he was responding to, why deliberately manufactured sadness feels rewarding rather than simply unpleasant, remains a genuinely open one in the philosophy of art today. One influential modern explanation leans on the protective distance fiction provides. A reader who knows, at every moment, that the heartbreak on the page belongs to an invented character can feel the full emotional weight of that heartbreak without facing any of the real consequences that same grief would carry in an actual life. The practical fallout, the ongoing responsibility, the changed circumstances that make real grief so much harder to simply sit with. Fiction offers something rarer than escape from feeling. It offers the feeling itself, in a form safe enough to fully experience, rather than instinctively guard against. Other explanations point to the pleasure of a well-built story structure itself, a satisfaction of watching tension rise and resolve, regardless of whether the specific emotion involved is joy or sorrow, or to the sense of meaning and insight sad stories often carry, a kind of emotional rehearsal for real losses still to come. Whatever the full explanation turns out to be, people keep returning to stories built specifically to hurt, and keep calling the experience afterward one of the better ones they have had all year. Physicists have spent decades cataloging the handful of fundamental numbers that seem to govern everything in the universe. The exact strength of gravity, the precise mass of a proton, the specific rate at which the early universe expanded. Nudge several of those numbers by even a small amount in either direction, and the consequences are not subtle. Stars stop forming, or form and burn out too quickly to matter. The particular chemistry that makes complex molecules and eventually life possible simply does not work. In many of these adjusted universes, nothing capable of noticing any of it would ever come into being at all. The actual values, the ones that happen to sit in our universe, land squarely within the narrow range needed for atoms, stars, and living things to exist, and nobody has a settled explanation for why. The astrophysicist Brandon Carter named the underlying idea the anthropic principle in 1973, and at its core, the observation is really a piece of careful logic, rather than a mystical claim. Any universe capable of being observed by someone necessarily has to have the properties required to produce that someone in the first place, whatever the odds of landing on those exact properties might otherwise have been. A universe with slightly different constants, one where no observers ever arose, would simply never be observed by anyone wondering about its constants. So it is no deep coincidence that the one universe we do find ourselves inside happens to be one where the numbers worked out. Physicists remain divided on what, if anything, this logic actually explains. Some take it as weak supporting evidence for the idea that a vast number of other universes exist, each with its own different set of physical constants, most of them empty and unwitnessed, with our own simply being one of the rare ones where the numbers happen to align. Others suspect the apparent fine-tuning will eventually turn out to have a more direct physical explanation, some deeper underlying law that forces the constants to land exactly where they do, with no need to invoke other universes at all. Either way, the universe we find ourselves looking out at from inside it is, by simple necessity, one where the looking itself was always going to be possible. 50 paradoxes, and not one of them was ever actually broken. A donkey between two piles of hay, a ship with none of its original planks left. A coin flip that promises infinite winnings nobody will pay much for. A night sky that stays dark instead of blazing with starlight. Each one sat patiently at the exact spot where a simple rule ran into a stranger world, and simply refused to resolve on command. Maybe that is what a paradox actually is, once you sit with enough of them. Not a mistake waiting to be caught and fixed, but a small, honest seam showing exactly where an idea that works nearly everywhere finally reaches its edge. Rational choice runs into a donkey that cannot choose. A tidy average runs into a hidden variable nobody accounted for. A single number, a coastline's length, a room full of birthdays, a set of all sets, turns out to depend entirely on the question being asked of it, in ways nobody thought to check until somebody finally did. None of these were really about ships, or donkeys, or coins, or envelopes. They were about the gap between a rule simple enough to state in one sentence and a world too layered to ever quite fit inside it. That gap has been sitting there the whole time, in grocery aisles and voting booths, and physics labs and family road trips, waiting for someone patient enough to notice it. You do not have to resolve a paradox to be changed by spending time with one. Some of history's sharpest minds gave an entire career to a single one of these and left it standing, unresolved, exactly where they found it, a little wiser for having tried anyway. The world keeps running on rules that mostly work, right up until every so often, in some quiet corner they do not. That is not a flaw in the world. It might be the most honest thing about it. Wherever you are when this reaches its last sentence, the paradoxes will still be there tomorrow, patient as ever, in no hurry to be solved.